All right, so I've already spoken a little bit about tilt rotors and how Wright One can help tilt rotors, especially during the transition state going from helicopter mode into a vertical flight path. But now I want to talk a little bit more about the efficiency in terms of our ducted fan solution and having a contra rotation as compared to other types of ducted fans that are on the market. So, let's talk a little bit about drones. You see a drone, it's got an open prop configuration. This one is actually taken from Skydio's website. And just for clarification, an open prop is something like what you would see on a drone, where the propeller is completely naked outside. Here's another example on one of my favorite aircraft. It's a Piper Aztec. This is me at the age of 12, actually in front of the Piper Aztec. Um, and if any of you know me, my favorite number is 54259, which is actually the registration number of that aircraft. Just a fun fact. But here at the bottom right is an example of a ducted fan. The one thing that you'll notice is that this is not like a traditional jet turbine, which is what we've been talking about a lot on these YouTube videos. So a ducted fan is actually just a fan. Think of like a hovercraft. Think of a desk fan that is just blowing air. The only thing that's different between the open prop solution at the top left with Skydio's drone and this particular solution is that there is a ring that is around the propeller. And the reason for this is because there's actually a higher efficiency gain when it comes to a ducted solution versus an open prop solution. So here are a few ducted fans that we can go over. At the very far left, you can actually see a ducted fan that's underneath the wing. This has zero compression. So compression being the key term there. Whenever you're compressing the air, you're actually doing work on the air with each preceding stage, and there is zero work that's being done on a ducted fan. Versus the next photo, which is a jet turbine, which is what you see on commercial aircraft. Now, this is slightly deceiving because that fan blade is the forward fan blade to a series of fan blades behind it. And so there is compression or there is work that is being done on every single stage as air moves through the engine. So moving more towards the right, this particular fan is on Lilium's electric jet. One thing to note here is, and this is also the same thing with Whisper Aero. Both Lilium and Whisper Aero have they've got shaft-driven electric motor systems. That's the key thing to note there, is that with the Lilium electric jet, you have a rotor that's in the front, and you can kind of see this. It's the cutout rotor, and then you have a stator that is actually housed around the electric motor for the Lilium jet. I believe the same construction is actually done for the Whisper Aero as well. The only difference between the two products is that one is acoustically quieter than the other, which Whisper Aero, I mean, the company name is a derivative of their byproduct or their product, which is their motor is incredibly quiet as compared to other electric motors that are on the market today. Still shaft driven electric motor systems. So there's compression that's actually happening because there's a rotor and then a stator because the air is getting corrected from the curl, but not as much compression as what's being done with a traditional jet turbine. Okay, so this video is just to show you kind of the differences between an open prop and a ducted prop.
During hover, open rotors are between 85 and 90% less efficient than well-shaped ducted fans at the same disk load, since nearly all blade tip losses and swirl losses are removed thanks to the duct and the presence of stator vanes. The two main disadvantages of ducted fans are higher power requirement. Because of the higher disk loading, the hover power consumption is higher than for open propeller aircraft. Additional aerodynamic drag and weight. The duct generates drag during cruise flight and increases overall weight.
Okay, and then this video is actually showing what a variable pitch prop is. Variable pitch props are actually really important in today's aircraft right now because what it does is it keeps the prop from actually overspeeding itself during certain attitudes of flight. So I basically just wanted to show you guys this video just to show that we have the technology today in terms of actually adjusting the pitch prop or the pitch of the propeller during flight.
Does your propeller blade make with the air as it chops through it? Let's say we're flying a Piper Arrow as an example. Just like a wing produces lift to counteract weight, the propeller produces thrust to overcome drag. And just like the wing, the propeller's angle of attack helps determine how much thrust is produced. A prop with a low angle of attack, where the blade is more or less perpendicular to the direction of flight, won't produce much thrust. But because it's at such a low angle, it can push through the air faster using the same amount of power, thus giving us more revolutions per minute. This is ideal for takeoff and climb when we want as many RPM as we can get. A prop with a higher angle of attack will take a bigger bite of air with each rotation, but the added drag will reduce RPM for a given power setting. This is fine for cruise, where the extra RPM doesn't get us extra speed and so it's more efficient. Think of the different prop angles like gears on a bicycle or a car. When you're starting from a stop or going up a big hill, you want a low gear. You'll pedal faster and have a higher RPM with less speed, while on a flat surface, as you speed up, you'll want a higher gear, more power with fewer RPM. A fixed pitch propeller like on a Cessna 172 is basically a compromise between a climb and cruise angle. But on some aircraft, like our Piper Arrow, the propeller blade angle can move during flight based on different circumstances.
So the key thing to note here is that we have the technology not only to adjust the pitch of the propeller, but at the same time, depending on the flight circumstance, uh, whether we're going through cruise, where we want a high pitch, where it's actually taking a larger chunk of air out during each swing of the prop, or if we're taking off, where we want a low pitch, where it's reducing the drag, but also having or enabling a much higher rotational speed so that we can actually climb out. These just vary the dynamics. I mean, the same thing is with helicopters. Helicopter rotation is around 150 RPM, especially at hover mode. And a lot of that has to do with just the blade pitch. You actually pull the collective to be able to actually make that happen. So merging the two of these in terms of actually getting the correct flight dynamics is the perfect opportunity for Wright One solution. All right, so let's go back to actually talking about drones again. So we've already discussed what an open prop can do, and we've also discussed what a variable pitch prop can do, but now let's talk about the Wright One solution. So I just kind of I didn't invert this graphic. I just kind of rotated this graphic in the way of saying that, let's stick a turbine or the Wright One turbine onto each one of those four locations for a drone. And what is the solution here? Well, for Wright One, what you're able to do is you can actually customize your drone to only be in hover mode specifically, and you can actually tailor the slots without actually having to change out the prop. What does that mean? It means that you can actually have multiple different types of configurations inside of your nacelle, inside of the core of the product, and you can have the engine itself tailored in terms of performance because nothing is connected to the central shaft. Everything is a direct drive electric motor system, meaning that you can get a power that is 1-to-1 and you can maximize the duration of the battery, and you can also have higher pitch inside the engine to be able to tailor it for cruise as well. You just turn on a couple of the fan stages and have air flow through and get worked in that particular regard. That's the power of the Wright turbine. So what we've come up with is a modular, customizable, expandable platform for all eVTOLs. And we don't have to actually go through an R&D program or project that costs billions of dollars for one specific aircraft to be able to put it onto your airframe. It could be any type of airframe. as well as the fan stages that you could slot into each individual nacelle to be able to get the customized performance that you're looking for your craft. That's the uniqueness. That's the value proposition of Wright One. No longer do we have to have so much dedicated to one solution for one aircraft. Wright One has actually done all the R&D effort up front. And now we can actually just place it in terms of customizable performance across all eVTOLs moving forward.